Approaching its initial years of scientific operations, the James Webb Space Telescope has profoundly altered our understanding of the universe. However, the telescope is posing significant challenges for scientists as it reveals inconsistencies in our cosmological theories. For decades, the story of the universe was thought to be well established. It began 13.8 billion years ago with the Big Bang, followed by a gradual evolution from simple to complex structures. This narrative, a cosmic progression from elementary particles to mature galaxies, suggested the earliest galaxies would be small and disorganized. The James Webb Space Telescope was launched to capture images of this era, but what it has found is calling this fundamental understanding into question. The ancient galaxies it has observed are too large and too mature, presenting a discovery so profound it may require a reevaluation of our standard cosmological models. To understand the earth-shattering nature of Webb's discoveries, we must first appreciate the model scientists constructed over the last century, the Standard Model of Cosmology, also known as lambda-c/dm. This model has been remarkably successful, postulating that the universe is composed of approximately 5% normal matter, 27% dark matter, and 68% dark energy. Dark matter provides the gravitational scaffolding for galaxy formation, while dark energy drives the accelerating expansion of the universe. Within this framework, the model predicts a specific timeline for galaxy formation. Following the Big Bang, it took hundreds of millions of years for gravity to assemble the first stars from primordial gas. This process, termed hierarchical formation, dictates that small structures merge to form larger ones. Therefore, the first galaxies should have been small and chaotic, gradually colliding and merging over billions of years to form the large, structured galaxies we observe today. This bottom-up construction was a foundational concept, and it was expected that Webb would provide definitive proof by observing these nascent, messy galaxies at the dawn of time. Even before the launch of the Webb telescope, there were indications of inconsistencies within our cosmological theories, the most significant of which is the Hubble tension. In simple terms, astronomers have two primary methods for measuring the universe's current expansion rate, the Hubble constant, and these methods yield conflicting results. The first method examines the local universe using standard candles, like Type 1a supernovae. By measuring their apparent faintness, their distance can be calculated, which, when combined with their recession speed, provides an expansion rate. This local measurement consistently yields a value of around 73 kilometers per second per megaparsec. The second method analyzes the cosmic microwave background, CMB, the light left over from the Big Bang. Using the Standard Model, scientists can predict today's expansion rate from this ancient light, which results in a value of about 67 kilometers per second per megaparsec. This discrepancy, while seemingly small, suggests that either one of the measurements is flawed or the Standard Model of Cosmology itself is incomplete. For years, the scientific community has debated this issue. The James Webb Space Telescope, with its unparalleled precision, was intended to resolve this tension by refining the measurements of these standard candles. When Webb addressed the Hubble tension, the results only deepened the mystery. In 2024, one research team, led by Wendy Friedman, produced new, high-precision measurements that resulted in a Hubble constant of around 70 kilometers per second per megaparsec. This value sits uncomfortably between the two previous figures, potentially reconcilable with the CMB prediction when uncertainties are considered. However, other Webb-based studies have continued to support the higher value, thereby intensifying the debate rather than settling it. While the Hubble tension was a primary focus, Webb made another, more radical discovery. In deep-field observations, astronomers pointed the telescope toward the early universe, expecting to find the faint smudges of the first small galaxies. Instead, they discovered what some have termed universe breakers, 6 candidate galaxies that were unexpectedly massive and mature. Seen as they were just 500 to 700 million years after the Big Bang, some of these objects appeared to contain as much stellar mass as our own Milky Way galaxy does today. This finding came as a bewildering surprise to astronomers, as it directly contradicts the gradual, hierarchical growth model. According to established theories, there simply had not been enough time for such massive galaxies to form. As astronomer Joel Leha stated, "We expected only to find tiny, young, baby galaxies at this point in time, but we've discovered galaxies as mature as our own." It calls the whole picture of early galaxy formation into question. This is a genuine paradigm shift in our understanding of the cosmos. It is moments like these that make science so thrilling, when a single observation compels us to re-examine our most fundamental theories. If you find this journey into cosmic discovery as compelling as we do, take a moment to subscribe and join our exploration of these universe-altering findings. The existence of these massive early galaxies presents a fundamental problem for the Standard Model. It should take billions of years for gravity to gather enough matter to form a galaxy with a mass of 100 billion stars, yet Webb has found them fully formed when the universe was less than 1 billion years old. This has prompted a re-examination of cosmological principles, leading to several new, if radical, theories. One possibility is that early star formation was far more efficient than previously believed. Some theories propose bursty star formation, where primordial galaxies experienced short, intense periods of starbirth, allowing them to grow much more rapidly than is typical in the modern universe. Another explanation is that some of these objects are not just massive collections of stars, but are instead powered by actively feeding supermassive black holes at their centers, making them appear deceptively bright. However, this leads to another profound mystery: the existence of supermassive black holes in the infant universe. Webb has confirmed black holes weighing millions to billions of times the mass of our Sun as early as 470 million years after the Big Bang. The conventional growth model, which begins with the collapse of a single star, is too slow to account for such massive objects so early in cosmic history. This has given rise to the theory of direct collapse black holes, which posits that under the unique conditions of the early universe, immense gas clouds could have collapsed directly into a massive black hole seed of tens or hundreds of thousands of solar masses. In 2025, observations of a unique structure nicknamed the Infinity Galaxy provided what may be the first evidence of such a direct collapse event in action. These observations are also pushing some scientists to reconsider more fringe theories, such as modified Newtonian dynamics, which suggest gravity behaves differently on galactic scales. The fact that some of Webb's findings align with certain MOND predictions is generating new discussion. There is even speculation about dark stars, a new type of star potentially powered by the annihilation of dark matter. The James Webb Space Telescope was constructed to answer fundamental questions about the universe's origins. Instead, it has dismantled old certainties and presented a far more complex puzzle. The story of the cosmos is being rewritten. While the Big Bang itself is not in doubt, our assumptions about the events that followed appear to have been overly simplistic. The early universe was not a quiet nursery of slow growth. It was a factory capable of producing colossal structures with astonishing speed. It was a place where supermassive black holes could be born from collapsing gas clouds, and where galaxies were already clearing the primordial hydrogen fog just 330 million years after the beginning of time. Webb has not broken cosmology. It has broken it open. It has revealed that our prior understanding was merely a first draft, and that the universe is far stranger and more magnificent than we had believed. The telescope has not provided the expected conclusions, but has instead offered a thrilling new beginning. The search for answers is just getting underway. Thank you for joining this journey to the dawn of time. If you wish to stay on the cutting edge of cosmic discovery, please subscribe and enable notifications. What do you believe these discoveries signify for the future of cosmology? Share your thoughts in the comments below.